the inner membrane of the mitochondria, called the cristae. So these are mostly protein complexes, which are multi-protein complexes. Of course, there's a couple that are soluble, and we'll talk about those. You are looking at redox reactions. Something is grabbing an electron and donating an electron. So anytime someone is grabbing an electron, something else must be losing an electron. So you always have oxidation and reduction together. As electrons are passed from protein complex to protein complex, they begin to lose energy. Some of that energy is harvested, some of it is lost as heat. And if you think of temperature regulation in your bodies, that's where the heat comes from. And in the absence of O2, none of this will happen because O2 is the final electron acceptor. Unless you carry out anaerobic respiration, in which case you still have electron transport, but something other than oxygen is the final electron acceptor. And we actually won't look at anaerobic respiration. So I have a few figures that are not from your textbook, so you have them on Blackboard. I put both small versions and large versions. You have simulations and figures in your textbook also. I kind of like these better. This figure shows you the changes in the energy levels of the electrons as they go from complex to complex to complex. So here's complex 1, which is where NADH donates its electrons. And then there's complex 2, which is where FADH2 donates its electrons. Notice complex 2, where FADH2 donates its electrons, is at a lower energy level than complex 1. So FADH2 electrons are at slightly lower energy level than NADH electrons are. Both complex 1 and complex 2 then donate their electron to ubiquinone. Ubiquinone donates its electron to complex 3, which is at a lower energy level. Complex 3 donates the electron to cytochrome C, and cytochrome C donates its electron to complex 4, which is also called the cytochrome C oxidase. So why would it be called the cytochrome C oxidase? What does an oxidase do? Yes, sir. So it's accepting an electron from cytochrome C, which causes cytochrome C to become oxidized. Therefore, this is called the cytochrome C oxidase. It's the protein that oxidizes that one. Then complex 4 donates its electron to oxygen to make water. So here's your final electron acceptor, oxygen, which is reduced to water. So at each of these steps, the energy levels of the electrons goes down. Some of that energy is harvested, some of it is lost as heat. So far, so good. Any questions? Before we take a look at what they actually do with that energy? Yes, sir.
Please explain to us the oxidase.
So the cytochrome C oxidase is complex 4. It's the protein that accepts electrons from cytochrome C, which means it oxidizes cytochrome C because it takes an electron from cytochrome C. So if you lose an electron, you're oxidized, and cytochrome C is now losing an electron. It's becoming oxidized. Therefore, this protein complex is called an oxidase. And then it will donate its electron to oxygen, which means it itself becomes oxidized, and oxygen becomes reduced to water. Yes, ma'am.
Could you say that they all oxidize each other?
So each one oxidizes the previous one, and each one reduces the next one. That is correct. The reason that we mentioned this one is because this one is a side of a specific inhibitor that we're going to talk about later. All right. So the way that your mitochondria actually makes use of the energy from NADH and FADH2 is through establishing a proton gradient across the membrane. And so as electrons are moving from complex to complex, in some places protons are moved also. And those happen to be complexes 1, 3, and 4. Complex 2 doesn't do that. But complexes 1, 3, and 4 move protons as they move electrons. So let's take a look at this figure, which shows you these complexes in the membrane and shows you the movement of protons as well as the movement of electrons. So we start with NADH on the left, donates electrons to complex 1. As complex 1 donates its electron to complex 2, to ubiquinone, a proton is moved from the matrix into the intermembrane space. So here's the inner membrane of the mitochondria, here's the outer membrane of the mitochondria. And as you move an electron from complex 1 to ubiquinone, Gesundheit, you move a proton from the inside to the outside. Complex 2 accepts an electron from FADH2, which then moves to ubiquinone, but no protons are moved. Notice complex 1 is a transmembrane protein. Complex 2 is not. To move a proton from the inside to the outside, you have to be a transmembrane protein. This one is not a transmembrane protein. Can't do that. Ubiquinone then moves the electron, donates the electrons to complex 3. And complex 3, also a transmembrane protein. When it donates its electron to cytochrome C, it will move more protons from the inside of the matrix to the intermembrane space. So here you have two places where protons are taken from the inside and moved to the intermembrane space. Cytochrome C is a soluble protein. It's going to donate the electrons to complex 4. And complex 4 will donate the electrons to oxygen. And as it does that, more protons are moved from the inside of the matrix to the intermembrane space. The reaction of oxygen with the electrons to make water requires protons. So you have oxygen plus electrons plus protons to make water. Which means when you make water, you remove protons from the solution here. So another place you establish the proton gradient is through the synthesis of water. So these three complexes move protons from the inside to the outside, and synthesis of water removes protons from the inside. All of them important in establishing a proton gradient. Where does the energy come to move all of these protons to the outside and create a high concentration of protons out here? The energy from the electrons of NADH and FADH2, as electrons are moving, they kept releasing energy. Remember this? The energy level kept going down, but they kept releasing energy. Those electrons keep releasing energy, and some of that energy is used to move these protons against their gradient. So complexes 1, 3, and 4 use some of the energy of the electrons to move the protons to a higher concentration in the intermembrane space. Synthesis of water removes protons from the inside. Complexes 1, 3, and 4 remove protons from the inside, and they add protons to the intermembrane space. You now have a high proton gradient. That proton gradient is very important because that's what you need to make ATP. While protons are not going to go back into the matrix on their own because they are charged. You need to provide a passageway for them. Well, lo and behold, there's a protein that does that, and that's the ATP synthase. The ATP synthase provides a passageway. Protons go down their gradient into the matrix, and as they do that, they release energy. And that energy is used to literally turn this knob. And that's actually mechanical movement of the knob. And a group in, I want to say Ohio State University, but I'm not 100% sure, several years ago, literally made molecular propeller by using this protein so that they could pump protons through them and have them turn. And that mechanical movement is used to actually then turn a DP, an inorganic phosphate, into ATP. So you have the movement of the electrons, the movement of the electrons releasing energy to move the protons, the movement of the protons releases energy to turn this, and that mechanical energy is then used to make ATP. And none of this would happen if you didn't have oxygen. No oxygen, no final electron acceptor, none of this happens. No oxygen, pyruvate does not go into the mitochondria, so this doesn't happen either. Without oxygen, pyruvate stays out in the cytoplasm. Yes, sir?
Can you go back to the complex 4
Here or the next one?
This one. What happens if the oxygen gets
So oxygen is going to be reduced to water. This reaction requires electrons and protons. The electrons are coming from complex 4, which got the electrons from cytochrome C, which got the electrons from complex 3, etc., etc. But you also need protons, and the protons come from the solution. And as you remove the protons from the solution, you bind them permanently to oxygen to make water to reduce the concentration of protons in the matrix. Moving the protons from the inside to the outside, removing them from the solution, all of that helps to establish the proton gradient. And the gradient is then used to make ATP. So I'm going to ask you to spend 2 minutes and explain this to the person sitting next to you. You will be given the figure on an exam, but you have to be able to talk about it.
Yeah, that's what to do.